Okay, so welcome back to the afternoon session today. Our next speaker is Christine Eagles from University of Waterloo, splitting differential equations using Galois theory.
Right, sorry, I forgot to turn that on. Okay, so a motivating example for this coming from the constants is if we look at a linear differential equation. So we have AI times some derivatives in y, and we take these AI to be equal to 0. And delta is some formal derivation, then its set of solutions forms a C vector space with basis v1 up to vk, say. And so we all know what this means, but the way that I want to write it is that if we look at any other solution to the system, then this means that we can find some coefficients coming from this field C, such that A lives inside of this field C, the differential field, together with our basis. And then even though these coefficients live inside of C, I'm going to write this here for emphasis, that we need them to define. So really every solution with the additional information of this basis comes from the constants. Okay, so there's a couple of things here. I haven't specified where we're taking our set of solutions. And also from a model theoretic perspective, we want to look at generic solutions, not just all solutions. So what do I mean by generic? So for us, a Colchin closed set B is the solution set of a system of differential, so I'm going to denote this by delta, of polynomials, which is defined over some differential field. Okay, so these are also sometimes referred to as delta varieties. And we say that this set is irreducible if it's not written as the product of any two proper closed Colchin closed sets. So if B is not equal to X and Y for X and Y proper Colchin closed. Again, everything here is over K. And so we're looking at generic points. So we say that the generic points of V over K are Colchin generic. So what I mean by this is they're of maximal dimension, or more specifically, these are all the points where X lives inside of V, but X is not inside of Z for any Z, which is a proper Colchin closed set, which again is defined over our field K. Okay, and then what this set here gives us, if we take collections of this condition or something which says I don't belong to a variety, this gives us our generic type of V over K. Okay, I will do this. Oh yeah, I can lift it. So collections of this form give us our generic type of V over K. So really what we'll do is we want to look at things which satisfy collections of equations of this form. Okay, so what we do to start with is we're going to fix U delta, which is going to be a big universal domain for algebra. So this is what we call a saturated differentially closed field of characteristic 0. And then inside, I want to fix a smaller, sub-differential field. So this means that the derivative restricts and the size of K is strictly less than the size of U. And what the saturated here is telling us is that for any consistent system of differential equations, which is defined over our small field K, there is a solution. So there is a solution A in U. So to look at there is a generic solution. So we don't need to take bigger field extensions to find solutions of the systems. So now when I say that we're looking at solutions to a generic type or generic solutions to a closed set, what I really mean is that we're looking at them inside of this field U. Okay, and then one last thing. So we will fix this curly script C, which is really a CU. So this is the field of constants of U. So I just want to emphasize that this notation dictates that we're coming from this field. So this is everything. This is equal to 0. Okay, so now we can define what it means to be internal. So if we let P be the generic type of some system of differential equations over K, we say that P is internal to the constants if we can find finitely many generic solutions. So I'm going to write this by this notation. So there's finitely many generic solutions of our system coming from U, such that if we look at any other generic solution, we can find finitely many constants such that A lives inside the difference field generated by this A1 up to AN together with these additional constants. Right, so our motivating example, this is internal to the constants, and really you can think of these, this finite set of generic solutions as acting like a basis. So we can weaken this notion a little bit, and if A instead lives in the algebraic closure of a collection like this, we say that P is almost internal to the constants. Right, so this is a weaker notion than being internal. So one example is if we let P be the generic type over K of the equation y prime equals 1 over 2y. So the solutions of this are of the form plus or minus the square root of t plus y for some transcendence element, which has derivative 1. So you can see that its solutions will solve a polynomial over some additional parameters, but they're not going to outright live in a field. So this is a weaker notion. Okay, so this is almost C internal, but not outright C. So internality is a bit rare. Yeah. Yeah, okay, maybe I might have wrote. Yeah. Yeah, I'm fixing a solution. Yeah, so what I really mean is that it satisfies, I think it's a minus here. Yeah, minus t. So that gives you a map.
Oh, okay.
Yeah. Yeah. Okay. So yeah, we don't expect internality and almost internality to happen all the time, even if you are related to the constants. So a kind of classical example is if we look at the system of y prime equals 0. So this equation, this gives us our derivative. So I will use the derivative here. So this gives us our constants. But then we ask that every solution to this solve this other equation. So if we look at this generic system, so this is not almost C internal. Despite the fact that on the face of it, it looks very related to the constants, right? It has the formula for the constants in it. So a kind of overarching challenge of model theory, or of this kind of question, is if you are given some set of differential equations, V over K, with a generic type P, again over K, can we determine if P is either outright or even almost internal to the constants? So the goal would be to develop an algebraic criterion for this outright. So this is obviously still a work in progress, but we can always look at specific subsets of our equation. And I just want to point out, and kind of verbally say, some different ways that people can think about internality or almost internality. So if we restrict ourselves to K being a subfield of the constants, then being internal to the constants is the same as taking your associated vector field. And after potentially taking a field extension, then you're birationally equivalent to a trivial vector field of appropriate dimension. So that's one way that you can relate this question. And a different way that you can relate being almost internal is that, again, after a base change or taking a field extension, then you have dimension V, many algebraically independent rational first integrals. Remember, these are rational maps which don't change along your vector field. So these are just some ways in which this question of internality can tie in to some of the other aspects of this week. Okay, but we're really going to be working with the internality framework and the internality language. So we're not going to answer this question today, but we can look at a sub-question. So really, we're going to be motivated by things that look like this example. Okay, so this has a special form, which is called the pullback by the log derivative of some equation. So what is the log derivative? So the log derivative is a map going from the non-zero elements of U to U. So this is a surjective group homomorphism whose kernel is the non-zero points of the constants. So we do have that this will be related to the constants inside of there. Okay, and this is the map where you take x and you map it to the derivative of x over x. So that is where this equation is coming here. So we really just ask for our solutions to be coming from a log derivative map. Okay, so for us, a Q is going to be the generic type over K of the equation where we take the mth derivative of y and we set this equal to some rational function in all of its lesser derivatives. So f is coming from k0 up to x n minus 1 m. I lost count of the indexes, but of the appropriate arity. Okay, and then we want to look at the pullback under the log derivative map of this. So we will take p, which will really denote this log delta inverse of q. So this is the pullback under the log derivative map to be the generic type over our differential field of the system of equations where we take the defining equation for q and then again ask that all of its solutions come from this log derivative map. So this is delta x over x is equal to y. Okay, so now the question, or a sub-question that we can look at is if we already know that the type that we're looking at is internal to the constants, then when is this pullback internal? So if Q is internal, then when is the pullback? Internal or even almost internal, which we've seen doesn't happen in general from this example over here. Okay. So there is one specific case where we will get this to happen. So this is when P can be thought of as a product. Okay. So how do we think of P as coming from a product? Well, if we take X and Y to be two irreducible, Colchin closed sets over some field K delta. Remember this field, oh, I think I didn't say it, but we do want to take this field K to be algebraically closed. So K here is algebraically closed. Okay, so because we have this as algebraically closed, then the Cartesian product of these is again an irreducible Colchin closed set. Is irreducible and Colchin closed. So to say that its generic type is a product, we really are just going to take the generic type of this. So I want to say that let's let Q be the generic type of X over K, and R is the generic type of Y. Then we denote Q tensor R to be the generic type of the Cartesian product. Okay, so this is what it means for our type to behave like a product or be a product. Okay. So then a kind of general example is if we were to know that Q and R are internal to the constants, and if P were to be outright equal to this, then P would have to be internal to the constants. So for example, if we take, okay, so let Q and R be generic types of some set of Colchin closed sets over K. And they're both internal to the constants. Then, if P is what we call interdefinable with the product, then P is itself C internal. So interdefinable means really that they're in bijection. So the definition I'll give is that if you take any generic realization for A, and P is also a generic type over K, then you can find some generic real, this should be a Q, sorry, Q, tensor R, then you can find some realization of this type such that the difference field generated by A over K is the same as the difference field of B with K. Okay, so as fields, they behave similarly. And now you can do something analogous for almost internal. Okay, so now we say that if P, maybe I'll go to the next board. Okay, so if P now is inter-algebraic with the product Q tensor R, yeah. So interdefinable means that if you take any realization of P, you can find some realization of this generic type. Oh, yeah, it's a slightly different definition. I was getting to that. But yeah, so inter-algebraic. So it means exactly the same thing. So if you take for all A realizing P, there exists a B realizing Q tensor R such that instead of now the fields being the same, the algebraic closure of the fields is the same. So instead of being in bijection, you're in a finite to finite correspondence. Yes, thank you. So this is, yeah, such that KA algebraic. So yeah, the idea here is that if you're interdefinable, so you have the fields the same, then you get internality from these two being internal. But if you only have inter-algebraic, so a weaker notion, then you get almost C internality. Yeah. For us, Q will be a one type, but we're thinking of P as the pullback, so P will be the two type over here, because we're really thinking of P as this type.
It's not a general statement about type P arbitrary final, right? But in general, the problem with Q and R,
yeah,
it won't be internal, right?
Yeah.
But it will be definable with Q and R.
Yes.
So P here is what? It's always the pullback. Oh.
Yeah, so I'm thinking of P as the pullback of this type Q, which will be this one type. And then
But this is a general.
Yeah, this is a general definition, but you can kind of think about,
Yes, that's right. But I mean,
Yeah.
the conclusion then P is internal.
mhm,
It's not always true, right? Q and R, I think. If Q and R is internal, I think the tensor product, the product, the way to find it, why is just P cross Q? Why is that internal?
Well, P is
Yeah.
identifiable with Q cross on it.
yeah,
But Q cross R is definable with itself, right?
We are both internal.
yeah,
Yes, both. Just saying that the product.
Yeah.
is internal.
That's true. I thought it was some sort of iteration, but.
Oh.
So the fact is the problem is one has to be independent of the other, right? So, okay, maybe I need to think about it, but
yeah.
thought it was like an analyzer.
No, that's, yeah, the products are internal. Okay. Yes, thank you for pointing that out. But yeah, in the specific contents that we're thinking, we're going to be taking P as this pullback and Q as this one type. Okay, yeah, no worries. Okay, so if we're inter-algebraic, then we can't include your internal, then we conclude that you're almost. C internal. Okay, so we're going to then turn this into a definition. So we're going to say that our type P splits if we can get something of this form. Okay, so if we now are back to our setting over there, where we're looking at P to Q, then we say this map splits. And we're asking, sorry, and Q is internal constants. So we say this map splits if P is interdefinable with Q tensor R for some, generic type over K R, which is C internal. And then to capture the almost internality, we'll say that this map, almost splits if P is inter-algebraic. With Q tensor R. Again, for some R which is internal. Okay, so then what this example really is telling us is that if you split, then you'll be internal, and if you almost split, then you will be almost internal. So the natural question is this an equivalence? So if you are internal, do you split? And the answer is no. So okay, so the converse is not, in general, true. So Jin and Musa, they gave a specific example where Jin and Musa found an example where P is C internal, yeah, C internal, but the map does not split. So the main takeaway from, so I'll come back to explain kind of what's happening here, but we can impose some conditions which will give us this if and only if statement. So we follow the techniques that were done in this paper where they introduce a form of splitting, and that requires us to talk about a model theoretic generalization of a Galois group known as a binding group. Okay. So binding group. We need our type to be C internal, but then we say that its binding group is this set of abstract automorphisms, where we take alpha to be a differential field automorphism of U, such that it fixes our set of parameters and the constants pointwise. And then we want to look at its restriction to our set of generic solutions. So what I mean here is the set of generic solutions of the Quotient closed set that this is the generic type of. Okay, so something nice about these binding groups is that there is an algebraic group G, which is given over the constants, such that as abstract groups, we can really think of our binding group as being the constant points of this group G. So we can really think of this as in terms of algebraic groups. Okay, so then what's happening with this example that they have here is that the binding group for the example that they picked up is PSL2, it's C points. So we need to somehow exclude something of this case. In fact, this has dimension 3 as a binding group. But okay, so one nice way that we can think about this is that if we have a map between our types, if we have 2 internal types, it would be nice if it lifted to a map with binding groups, and it does. So one other nice fact is that if we have our log derivative map from P to Q, and P is already internal to the constants, this forces Q to also be internal to the constants, and we get a surjective group homomorphism on our binding groups. So this goes from the binding group of P to the binding group of Q. And it behaves in the way that you would expect. So if you apply this to some automorphism over here and look at how it behaves on a realization of this type, well, that's the same as if you were to take log delta of wherever tau maps this A, where A is a generic solution to our system. Right, so it behaves nicely with the downstairs. Okay, so from this equation, or from this map, we can create a short exact sequence. And so it'd be nice if splitting over here agreed with our splitting definition for types. And we can get that under some conditions, if you split as a short exact sequence, then the log derivative map downstairs has to split as well. And that's what Leo and I showed. So we showed that if we have this log derivative map from P to Q, and we already know that we're internal, and hence Q is internal, and Q is something that's called weakly orthogonal to the constants. So what this means is that we have no new constants when we add solutions here. So the C, or constants of K, is the same as when we add in these B for any B realizing Q. And we have another assumption. So we proved it for a slightly more general condition, but I'm going to state this one because we will need it for a theorem later on. So we ask that the binding group of Q which we already know will be related to the C points of an algebraic group, we ask that G is a linear nilpotent algebraic group. So then if the short exact sequence where this group is our kernel, we have our binding groups of this induced map on the binding groups from the log derivative. So if this K definably splits, so what I mean by that is that you have some map S here, which witnesses your splitting, and this map is given over K, then our log derivative from P to Q must split. Okay, so it's a way to go from this short exact sequence to our map. So this is how we were using some of the Galois theory. So I don't think it's easy to check. In the case where you have like, if you're over the constant parameters, there is some characterization for when you're a minimal or strongly minimal type, what your binding group can, but it's not easy to check, no. No, Q doesn't need to be a linear differential. I don't think, I'm not sure. Yeah. 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 So kind of. Oh. And the equation? Yes, yeah, sorry, yes. Yeah. Yes, yes. Yes, sorry. Thank you. Yeah. Okay. Yeah, okay. But so we have this, and okay. So then we can show a more so under these assumptions, we can show the connection between internality and almost splitting. Okay. So this is our theorem. So we have the same assumptions as over there. We have that this is internal to the constants. Q is weakly orthogonal to the constants. And the binding group of Q, sorry, is again isomorphic to G, where G is a linear potent algebraic group. Then the following are equivalent. So we have one at the log derivative map of Q at Q. So if we take this to be P, the pullback, this is almost C internal. If and only if the log derivative map from P to Q almost splits. And then the third condition is a more algebraic condition, which comes from Jin and Musa. That's what they called splitting, but what we call product splitting. So product splits. So what this means is that you can find some non-zero integer and generic solution A and some W1 and W2 such that some power, the kth power of A is given as this product. A W2 comes from K, the differential field adjoined, or of K adjoined with this log derivative of A. And lastly, we have that the log derivative of W2 lands inside of our field K. So these conditions are super important for us to understand. It's just a much more algebraic condition. And so under these assumptions, all three of these notions agree. And what's important about the product splitting is that we can, from this, we can develop a more algebraic criterion to check this almost internality. So just a note, this example really shows that this does not hold in general. We do need some assumption on the binding group. And Leo and I produced an example of some generic type. So we have a type which is, so we have a type which is C internal, but the binding group, or sorry, but the map does not split. Or sorry, we did not produce an example. We showed that there exists something where this map does not split and its binding group is isomorphic to the C points of an elliptic curve. So we do need the linear assumption as well in here. Okay, so from this product splitting, we can deduce an algebraic criterion. But first, I want to say what had been done in the past to develop this algebraic, or to develop an algebraic criterion for this splitting. So some algebraic characterizations. Splitting. So Jin and Musa had looked at this for product splitting, and they found a criterion in the case where, remember that Q is the generic type for the equation of the mth derivative of y is equal to some rational function in all of its previous derivatives. So when m was equal to 1, k was a subset of the constants, so we're in an autonomous setting, and q was C internal. Then they developed a criterion for almost splitting, which also told us something about almost the internality. And then there had been some other work for splitting done by Jowie, Jimenez, and Calais, which looked at when m was arbitrary, once again in the autonomous setting, but now as a kind of different direction. Instead of looking at when Q was C internal, they looked at when Q is unrelated from the constants. So this means that every every field extension where you take what's called like a non-forking extension remains independent. So you're just very far from the constants is essentially what this condition means. And I'll point out that when m equals 2, these two conditions agreed. So what Leo and I did was obtain a partial generalization of these criterions. Again, via this product splitting. So as a corollary, if we look at our log derivative map from P to Q, where Q is C internal, Q is weakly C orthogonal, and again, our binding group comes from a linear nilpotent group. So this is GC, where G is linear, potent, algebraic group, then P is almost C internal if and only if we have this characterization where K times x0 minus E times H is equal to the derivative of H, which is some big long equation. It's 2, the partial derivative. So I should say here that we can find some rational function over K, which is non-zero. Some E in our field K, and some integer. So maybe I shouldn't use K here. Maybe I'll use N. Then this is equal to the derivative. So this is really a condition that we look at on F, which was in our equation for Q. So this is, we apply the derivative to the coefficients of H. So this part doesn't matter so much. And really, these things are coming from product splitting. So this is coming from the fact that A to the N will be equal to W1 times W2. This E is the log derivative of W2, and we ask that H of A for some solution be equal to W1. So this is kind of how we're using product splitting to get this. So again, it's a partial generalization because it does require some additional assumptions on the binding group. So yes, I'll end there. Thank you.
Any questions?